have started recording. Just give me 1 minute. Okay, anyway, I will start this. Uh, so one of the most important application of thermodynamics is making a non-spontaneous process spontaneous or vice versa. So as we know that this spontaneous or non-spontaneous depends on this delta G value. So if delta G is less than 0, then it is spontaneous. If delta G is greater than 0, it is non-spontaneous process. So if suppose a process is non-spontaneous, means delta G is positive, and if you want to make it spontaneous, then delta G should be greater than, less than 0. So idea will be to make delta G value from positive to negative. If you want to make a process a spontaneous process spontaneous, okay. The way we can do it is through effect of pressure, and that I have already discussed with you in the last lecture. So if if you remember, the equation was dg is equal to vdp, or if I calculate delta g by integrating this, assuming Vm is constant, then what we will get it, delta G is equal to Vm P2 minus P1. Okay, this equation is valid for liquids and solids, but for gases, uh, this V is dependent on pressure, and so if suppose a gas behaves as an ideal gas, then Vm will be RT by P, and then if you integrate at constant temperature, temperature can be taken out, and then you get this equation. So this is the equation uh, through which you can look at the effect of pressure on G value. Okay, so delta G for so take this reaction R going to P. So for that you need to write d delta G. If I am talking about here, I talked about effect of pressure on free energy of either reactant or product. Right now we will talk about of a process. For process, you have to look at how delta G changes, because for R to P you have delta G value, and that is nothing but dg of product minus dg of reactant, and d delta G will be, I know that dg of product will be volume of product into dp minus volume of reactant into dp. So d delta G will be, if I assume that volume is constant with respect to pressure. So this is for a reaction which is happening in solution phase. Then you will write Vp minus Vr dp, and so del delta G is delta Vd. Okay, so so pressure. So you can think of dp or P2 minus P1 if it is positive. What does that mean? That and delta V is positive, then delta G will be positive. So if I increase the pressure and if delta V is positive, then delta G should increase. But if delta V is negative for this process, in that case, delta G will decrease with increase in pressure. Okay. Now let's take one example. Here in the transition, for example, calcium carbonate to in aragonite form to carbonate in calcite form. Okay, so these are the two different phases of calcium carbonate. In this case, delta Gm is given as minus 800. It means that aragonite to calcite is a spontaneous process. Delta Vm is given. Am I right? At what pressure would aragonite become the stable form at 298 K? Okay. At let me just 1 minute. I don't know. Okay, anyway, so in the transition calcium, so what I was talking about, that this is a spontaneous form, it means that at 298 K, calcium carbonate is a stable form, and that's why this is this is a spontaneous process. Is there any question? Hello, do you have any question? Okay, no question, then delta Vm is positive, and so aragonite, when aragonite can become stable, that's what is the question. So suppose I want to convert calcite to aragonite, what we should do? So again here we can apply this equation. Since delta V is positive, what we need to make, if I want to make calcium carbonate in aragonite form stable, we need to have this as positive value. Then only I can make aragonite form more stable. It will not go to calcite. It will be non-spontaneous process. So we have to increase the delta G value. We know delta V is positive, and if we apply this equation, then we can understand how I can make this positive. So it is simple that with this equation, what does this tells? That delta V is positive. We know that. And if I increase this, so I expect delta G to increase. So you need to increase the pressure if you want to make aragonite more stable form. Is it clear? Any question here?
So what does double delta signify?
Okay, so what I told that if I talk about one reactant, then I talk about delta G. Okay. If I talk about a process, then I talk about delta G. So suppose I want to increase, just I'm only concerned about G of calcite. Okay. Then what we will do, we will look at, that's what I explained here. If you remember this, that if I talk about delta G, it is Gp minus Gr. And if I talk about delta G, I'm talking about change in delta G of this process. So there are two different things. One is only I'm looking at the effect on R or effect on P. Then we talk about delta G, how G of R changes with pressure. So that is delta G. How G of P changes with pressure, that is delta G. But if I am talking about this process, R to P reaction, any physical process or any chemical reactions, I am talking, we have to discuss how delta G changes, not how G changes. Is it clear?
Yes, sir.
Okay. So, so now you have seen that this kind of things, for example, if suppose if we are dealing with at what pressure, diamond is more stable. You know that with increase in pressure, graphite converts to diamond, right? So that is again a phase change. One of the phase of carbon is graphite, another is diamond. At room temperature, we know that graphite is more stable. So in that case, what you need to do is you need to calculate what will be the pressure at which carbon diamond form will be stable. Okay. This so again, any phase reactions or any phase changes can be understood by looking at the how delta G changes with pressure or temperature. Okay, so now let's think about in the last two slides I discussed about how pressure affects. Now I will discuss about how temperature affects the phase transition. Okay, this is the equation which we used, and this I have already discussed with you in the last class, but I will show you here one more time. So dg is minus sdt plus vdp. If I want to look at temperature dependence, then I take pressure constant. So what is left is dg is minus sdt at constant pressure. So del g by del t at constant pressure is minus delta s minus s, or del g by del t at constant pressure. So del gm, which is basically chemical potential. So you just understand that chemical potential is similar to molar Gibbs free energy. That's what we generally see, but since you probably would not have studied chemical potentials, so just keep in mind that it is nothing but molar Gibbs free energy, particularly for one component system. So del Gm by del T minus delta S, we know that Sm gas is greater than Sm liquid, and that is entropy, molar entropy of solid is smallest. And so what we expect is that free energy should decrease, because S is a positive quantity, should decrease with temperature. uh, it is equally true for gaseous form, liquid form, and solid form. Since entropy of gas is quite higher, and so you should expect that with increase in temperature, decrease in Gibbs free energy of gaseous form will be more steeper. Am I right? And that's what is shown here, and that I have discussed last time, that solid has lowest Gibbs free energy, means highest stability at 0 degrees Celsius. Then you have a liquid, and then you have a gas. So it will somewhere meet here, and this will somewhere meet quite up here. Okay, this is the way chemical potential or free energy. Let's talk about free energy, that is molar Gibbs free energy of solid will change. Here this will be much steeper, and for gas uh, most steep change you will observe. Am I right? So at one point, liquid free energy of liquid will become lower than free energy of solid. It means that liquid becomes more stable than solid, and that temperature is known as freezing temperature or melting temperature. All right. If you go to this side, this is freezing. If you go to solid to liquid, then it is melting. And then again at some higher temperature, chemical potential of free energy of gas will become uh, most negative, or you can say lower than liquid and solid. This temperature is known as boiling temperature. Okay, and that is simply because of this thing, right? That entropy of gaseous form is greater than entropy of liquid and entropy. So basically, a simple anything which you can think of. For example, nitrogen is a gas at room temperature, but it can be converted into liquid form, it can be converted into solid form. There will be some freezing temperature and boiling temperature. And every phases of a compound is can be used for a different purpose. For example, gaseous nitrogen is quite often used to create an inert environment. If you don't want oxygen, then that can be done. Then you see liquid nitrogen. Liquid nitrogen is used to decrease the temperature. Uh, for example, if you have heard NMR, NMR temperature maintained through liquid nitrogen. So every form of a compound is has some application. For example, CO2 gas, CO2, then this CO2 liquid form. CO2 liquid form can be used for different purpose. CO2 in solid form is known as dry ice, and that can be used for different purpose. Okay. Similarly, this is the phase changes of a compound uh, in solid, liquid, gas form. Even in solid form, there can be different phases. For example, calcium carbonate we just discussed. It has aragonite form and calcite form, and both have different applications. So again, here you can look at the phase changes. Okay. Okay. Anyway, so this is the effect of temperature on free energy, and this is what is known as Gibbs-Helmholtz equations, and this is the equation delta G2 by T2 minus delta G1 by T1 is equal to delta H1 by T2 minus 1 by T1. So effect of temperature will depend on delta H value, and I discussed that with you in the last lecture, that if it is exothermic, lower temperature will make if you decrease the temperature, then a non-spontaneous process can be made spontaneous. So for example, if delta H is greater than 0 and delta T is greater than 0, then so if it is a endothermic process, delta H greater than 0 means endothermic process, am I right? If I increase the temperature, then delta G2 will be less than delta G1. Delta G2 will be less than 0. Delta G1, that tells you that an endothermic reaction will become spontaneous on increasing the temperature, whereas an exothermic reaction becomes spontaneous on lowering the temperature. Is this okay? This we have already discussed in the last class, but through equation you can understand it much better. Is this okay? Any questions here?
So what does delta G2 and delta G1 denote? Like 2 and 1, reactant and product?
Okay, so delta G2, and what does delta G2 denotes, and delta G1? That's what is the question?
Yes, sir.
Okay, so delta G1, so if T at T1, value of delta G is shown as delta G1, and at T2,
So delta G of the reaction, right?
delta G of the reaction, you are right.
Okay. Thank you, sir.
So a reaction, have different delta G at different temperature. So delta G for a reaction, that I am so delta G1 is basically delta G at T1, some temperature T1, and delta G2 is delta G at temperature T2. Is this okay?
Yes.
Any other question? No? Okay, so this is the effect of temperature. Now, next thing is, so till now we talked about effect of temperature and pressure on delta G value. But now look at effect of pressure on melting point. So pressure at temperature. So effect of pressure on equilibrium temperature. That's what we are going to look at. So effect of pressure on melting point of freezing point. Am I right? And that also I discussed last time. Okay, so this was the thing. Response of melting temperature to applied pressure. So this is suppose at one pressure. Am I right? This is one pressure. This is for solid form, and this is for liquid form. And we know that this is the temperature which is known as freezing temperature. So this is how delta G changes with temperature for solid form. This is how delta G changes with temperature for solid form, and this is your freezing temperature. Right? Now, if I increase the pressure, depending on Vm, okay, so Vm generally Vm of liquid is greater than Vm of solid, and so here increase will be smaller and here increase will be larger. All right, this is for solid liquid and this is for solid. So you see here, if I increase the pressure, and that's what it is written, this point is at lower pressure, this point is at higher pressure, so it increases because Vm is always positive, so G will increase, but increase will be smaller for solid form and increase will be larger for liquid form. And then you just, if you draw this, you will see that freezing temperature increases with pressure. This is for normal liquids. Now look at water. In water case, Vm of solid is greater than Vm of liquid. In that case, here there will be larger increase, and at this point there will be a smaller increase. It will always increase, but magnitude of increase will be different for liquid and solid form. For water, the increase in free energy will be smaller in liquid form than in solid form. And that's why if you draw this, you will see that the freezing point decreases. So with increase in pressure, freezing point decreases for water. For other liquids, it increases. So please keep that thing in mind. And that's why water is a very unique liquid. All right. Okay, and that's again I discussed that as we glide across the ice, we exert pressure on the thin blade. So there is a thin blade here, and are therefore creating a small stream of water in our path by melting that ice. The water between the blade and the ice is what we really glide across. So there are a lot of applications, and we need to understand applications uh, because then only you will appreciate, physical chemistry. Okay, now next is here we looked at effect of pressure on melting point and freezing point. Now you can look at effect of pressure on boiling point. Same thing now we are drawing. Right now we will look at just effect of so suppose this is a liquid and this is the gas. Right, liquid will decrease with the smaller rate in comparison to gas, and gas is always, there are no exceptions here. Gas is going to have more volume in comparison to liquid. Okay, so there is no exception here. And so what you will expect that with the increase in pressure, there will be shift towards higher temperature. So boiling point of the water will be raised. Okay. If the pressure above water is increased, it is lowered if pressure is reduced. Okay. And so what we knew now, boiling point of water is raised if I increase the pressure, and that is on this basis your pressure cooker works. All right, what we are doing, we are increasing the pressure, and that's when water will now not boil at 100 degrees Celsius, it will boil at higher temperature. Okay, it will boil at higher temperature. And so, so anything inside this will be cooked more easily because temperature of water will be high. So an application of this effect is pressure cooker. A pressure cooker traps steam inside it, raising the pressure to about twice the atmospheric pressure. As a result, water boils at 120 degrees Celsius. Maybe this is a bit higher, maybe it is less, but anyway, it makes boiling point higher. So food cooks quicker at higher temperature. Okay, so autoclave, that's what I discussed last time, the application of this autoclave. This is the basically used to sterilize things. So either in pathological lab or some labs who are working on in biochemistry area, they have this autoclave because everything need to be sterilized. Okay, and again here the pressure, due to pressure, increase in pressure, water boils at higher temperature. Studying virus, somebody is studying protein, or somebody is studying. So then they need to use this. This sterilization is usually done in a device called an autoclave. Essentially, an autoclave is a container that exposes the material to be sterilized to temperature above the boiling point of water, which is achieved by increasing pressure. Okay. So this is the second. So I told you about two different ways to increase the delta G or decrease the delta G, one through temperature, one through pressure. And then I also discussed about how pressure affects the boiling temperature. And similarly, you can also look at the effect of temperature on vapor pressure. Okay, same way. You can go and look at effect of temperature on vapor pressure. Now I will go to discuss another way in which you can affect delta G or G of a reactant or delta G of a process, and that is addition of non-volatile solute. And this is the basis of your this colligative properties. Okay, so this is because of, again, colligative properties is because of free energy change on addition of a non-volatile solute. And here is the equation. I will not go into detail. What is given here is the chemical potential, which is nothing but molar gas free energy changes with mole fraction of, this is for liquid, mole fraction of uh, your solute. Okay, mole fraction of solute. Since mole fraction is always going to be less than 1, and so this quantity is negative, and so chemical potential or gas free energy of a liquid decreases on addition of non-volatile solute. Okay, non-volatile solute. So you can understand, if I want to decrease the chemical potential, I should add a non-volatile solute. I should add a non-volatile solute. Okay, so chemical potential decreases with the addition of a non-volatile solute. And now I will show by the picture. You just remember this. You don't need to understand how to develop this equation. But now this diagram you already know. This is free energy versus temperature curve. This is for solid, this is for liquid, and this is for gaseous system. Right. So this is your freezing temperature. This is boiling temperature. Now what happens when you add a non-volatile solute? It doesn't affect the solid phase. It doesn't affect the vapor phase. What it affects is chemical potential of liquid. So pure liquid is higher and solution is lower. That's what we looked from the derivation which was done in the previous slide. right? So solution has lower potential energy compared to liquid. What happens then? You see that now it crosses this chemical potential of solid at a lower temperature, but it crosses the chemical potential of vapor at higher temperature. This is very means nice figure to tell you why there is a depression in freezing point, why there is elevation of boiling point. It is quite simple that chemical potential of liquid form gets affected on addition of non-volatile solute. Once you understand that, it is quite easy to understand why there is a depression in freezing point and why there is elevation in boiling. Is it okay? If you have any question, just let me know. Yes, any question, just let me know. Then I will proceed further. Am I audible?
Yes, yes.
Do you understand whatever I have discussed till now?
Yes, sir. Sir, I had one doubt
Yes, sir.
regarding some, yeah, regarding intuition. Like, used to say that because there's non-water solute in a normal solution, so boiling would become tougher because like there's competition between a normal molecule and the non-water solute. So similarly, can we give some correlation over here for delta G, like for
So you can understand that way, but what I am here discussing about, you see, if you go at molecular level, then you have to go to statistical thermodynamics. Thermodynamics, what it puts you is the macroscopic property. And I will discuss later that it is very difficult to tell microscopic property from the macroscopic property, because there are a lot of things going on. One factor will go in one direction, another factor will go to another direction. For example, just let me tell you that protein folding, right, or micelle formation. So protein folding, if you think about protein uh, getting from unfolded state to folded state, what do you expect entropy to become? Positive or negative?
sir, it will become entropy should uh,
Delta S will be
decrease.
will decrease. Am I right?
Yes, sir.
That's what you expect.
Yes, sir.
But for protein folding, delta S is positive. Yeah. So again, you have to go into detail, because what you are looking at just only protein folding as such, but there is a water molecule nearby. So what happens to water? That is also another thing to look at. So I will discuss a bit of that how even mechanism can be understood uh, through thermodynamics. Okay, so so there are a lot of different things going on. For example, if there is a two things binding, okay, we generally look at what happens to those two things, but we don't look at the environment. What is happening to environment? For
Yes, sir.
example, let's think about if I add a solute to water, okay, any salt to water. What do you
Yes, sir.
expect entropy to become?
So because solvation happens, entropy should decrease probably.
ये वाटर किसी चीज को दो चीज को मिक्स करोगे, what will happen to entropy?
That way it increases.
That will increase. So solute
Yes.
if you add to a solvent, its entropy will always increase, right?
Yes, sir.
But then why some salts are insoluble?
So that we give solvation the cause, right? If the energy
Yes,
released when.
enthalpy also matters, right?
Yes,
So,
sir.
so those things are very important to understand. Okay, but just remember one thing, that from the thermodynamics you can talk about macroscopic property. Yes, some mechanism can be known. Okay, for other things, for uh, looking at the detail why that is happening, sometimes requires use of statistical thermodynamics or quantum. Okay,
Okay,
so
sir.
please keep that thing in mind. Here we are dealing with like volume. We are dealing with enthalpy. These all are macroscopic property. But combining that to a microscopic property, then you have to go to a statistical thermodynamics or quantum. Okay. So please
Yes,
keep
sir.
that thing in mind. Here what we are saying, that if I want to affect the boiling point or any transition temperature, I have shown you just about solid to liquid or liquid to gas. But you can think about going from diamond to graphite or graphite to diamond, any phase change. And all the material science people, all they are working on phase changes, right? From one phase to another.
Yes, sir.
A superconductive, when I can go from conducting to superconducting. Those all are transitions.
Yes.
There's a lot of noise. Okay. Any other question?
So, like in formal cases, the graph was different for water, but in this case, it's common for everything, right?
Yes, you are right.
Okay.
So idea is simple. Only water is the exception where the volume of solid is greater than volume of liquid. But when you go from liquid to vapor form, the volume always increases. There is no exception. Okay, there is no exception. Only when you are talking about solid to liquid transition, there is exception. Water is unique. Okay, is it okay?
Yes, sir. Thank you, sir.
Okay, so now let us go ahead and think about what is the other application of thermodynamics can be. Okay, not only this was generally what we studied during our till now. What I was talking about is the things which we generally discussed in class 12. But thermodynamics is not only limited to that. In fact, we can also look at gravitational field, centrifugal field, or surface area on the property of the system. Here I mean again, transition temperature or pressure. For example, I will give you one case. Delta G is not only just minus SDT plus VdP, it also has component from what is known as extra work. Okay, extra work. So extra work can be due to height, extra work can be due to surface tension, extra work can be due to any other work than pressure volume work. Okay, so one thing is heat, another is work. Am I right? So here this mgdh will be giving you extra work. Okay, so if extra work is involved, what you can do, there are four equations for delta G, delta H, delta uh, U and delta A. You just add extra work. That's what. And at constant temperature, you will write VdP plus mgdh. and at equilibrium delta G is 0, right? And that's what we saw in case of suppose I just removed dWe or extra work, then what we have, delta G is minus SdT plus VdP. At equilibrium delta G is 0, and then you can look at the effect of pressure on temperature or effect of temperature on pressure. Okay, what when we say effect of pressure on temperature, I am talking about equilibrium temperature, or for example boiling temperature, or you know like freezing temperature. Similarly, I can look at the opposite way, effect of temperature on vapor pressure. Okay, and now if I include the extra work, then I can look at the effect of height on vapor pressure. So now you can know if I go up or if I go down, what will happen to vapor pressure. For example, here I have shown you to calculate the vapor pressure with the height. And what you can look at, it is simple, integration, and that's what is shown here. So if this is delta H is positive, delta H is positive means this part is negative. It means vapor pressure will decrease, right? And that explains why water boils at 70 degrees Celsius up in the Himalaya. So water boils only at 70 degrees Celsius. And so you can understand why cooking is so difficult at the, when you go up. And similarly, if you go down, you can expect what happens to, uh, you know, this boiling temperature. What happens to vapor pressure, and then you can understand what happens to uh, your boiling temperature or melting temperature. So this is one thing. Now you can think about if there is a suppose surface tension thing, then what will happen? And that based on that, this equation has been derived. It tells you effect of surface tension on surface axis. Okay, with the concentration, what happens? Okay, so I will not go into detail, but idea is to tell you that it is quite simple. At equilibrium, this will be 0. And so you can look at the effect of other things on boiling temperature or vapor pressure, vapor pressure. And that's why, scope of thermodynamics is unlimited. If you have, for example, if you have both height and like uh, if you are adding something, for example, non-volatile solute, then there will be a chemical potential term here also. Okay, so this is quite here the addition will be quite exhaustive. Any kind of work can be included here. Work due to area change, work due to means like height, and then work due to if you are suppose if there is suppose a rubber band and you are trying to or a spring, you are trying to compress it, or you are trying to elongate it, there will be a work done. And then from that you can look at the effect of this. Okay, so here this thing basically tells you about how to gives you idea how to stabilize suppose a protein in a lab. For example, what does this tells? This is your surface tension, this is surface axis. So if a solid increases so LNC here is the concentration, and this is surface tension. If solid increases the surface tension of water, its surface axis will be negative. So this kind of things you can even understand. What I mean by surface axis, now you can see it here, that within near the surface, this added thing is in less number than in the bulk, and that is known as surface axis. And in this case, particularly in this case, this is negative. What that mean is that this solid will be preferentially excluded. Okay. So, if you go another thing, then that can talk about equilibria of this. And what does it tells you? I will not explain in detail, but what is does tell you that if it is preferentially excluded, the solid which is preferentially excluded will stabilize the protein. Will stabilize the protein. Okay, so these are the few of the examples which I discuss. This I will not discuss. Let me go another. I will discuss a bit of phase transition.
Sir, I have a doubt in that surface axis example.
Yes, yes. Tell me.
So like so over here the solute will be like in general the colored one will always be the extra thing which is added. So if the surface axis is positive, won't it eventually be something like that the solute itself has changed? Like if it's positive, because then the
This is,
entry.
this is, this is non-specific interaction. And so what happens, there are two. For example, if I take surfactant, okay, let's give me one example. Surfactant. What surfactant does? It decreases the surface tension. Then there will be more it here. Okay. If there is more here, then what will happen? That will basically bind to this protein, that is called preferentially binded, a bond. Okay, preferentially bound.
Yes, sir.
This is called preferentially excluded. Generally, if it preferentially bound, that state, that thing will get stabilized. In a simple term, just remember that if you bind something to a reactant or product, it will be stabilized. Now look at this picture. I will just explain through that. And this is the equation which tells you basically about that what happens to equilibrium constant. But in simple term, layman term, if it binds to this, then it will stabilize reactant. If it binds this, then it will stabilize this one. Am I right? And since this is non-specific binding, so if you look at the protein, this is the protein folded state, this is protein unfolded state. Now, which one is a more surface area, larger surface area?
Unfolded.
The unfolded form. So it will bind to unfolded form more. It means it will stabilize this stage more. Am I right? It means the
Yes.
equilibrium will be shifted towards right hand side.
So
So
but then
protein becomes unstable. Okay, so surfactant basically destabilize the protein. Yeah, now you go ahead. Ask question.
so but in this case the surface axis would be positive, right? Because it's bounding, like it's binding the.
Yeah, that's what I'm saying. So if
Yes, sir.
something bounds here, preferentially bound, something which decreases the surface tension, it means it will bind it will bind to both states, but binding will be more in the unfolded state,
Expand.
and so reaction will shift towards right hand side.
Yes, yes, sir.
And so basically protein gets destabilized. You go opposite way. If I look at the which solutes which increases the surface tension, am I right? In that case, it will be excluded. So exclusion will be more here, am I right? In
Yes,
comparison
sir.
to protein. So
Mhm.
equilibrium will shift toward left hand side. It means this state will be more stabilized, and that is folded state, which is active state. Is this
Yes,
okay?
yes, sir.
Yeah. Anybody, since now it is more than 11:50, so anybody, if they have question, please ask.
Sir, please explain again the effect of surface tension.
Okay. So this is well known. This is known as this equation which I showed you. It is known as Gibbs adsorption isotherm. Okay. And that you can look at how that has been derived, but this is simply derived using uh, this equation. Okay, minus SdT plus VdP, there will be a chemical potential term, and then there will be your gamma dA, which is surface tension multiplied by change in area, because we are taking extra work which is due to change in area. Okay, and that is basically so. So again, at constant temperature pressure, this will become zero, but you have these two quantities to look at. And from that, you can derive this equation, which is known as surface excess, which tells you about how many, what is the solute, means solute concentration nearby is this in comparison to the bulk. So for example, here, if you look at in bulk, there is more solute in comparison to near the surface. And then in that case, surface excess will be negative. Okay, surface excess will be negative. So now look at this equation, what that this tells you. This is surface, how surface tension changes with change in concentration, right? So if suppose something which increases the surface tension, it means this will be positive, and so surface excess will be negative, and that's what is shown here, right? A surface excess will be negative, then it is called preferentially excluded from the surface. Okay, so that is one case which I discussed. Okay, is it clear here? Am I right?
Yes, sir.
Okay, is it clear? So now I effect of concentration on equilibrium constant, but I will not go with that. I will, in layman language, I just wanted to explain you, if something binds to suppose reactant, and this is well known thing, that if I want to shift the equilibrium towards this side, I add something which binds to reactant. And if I want to shift the equilibrium towards right hand side, then I add something which can bind to the product. Okay, this is well known. So if something binds to reactant, the equilibrium will shift towards left. If something binds to product, then equilibrium will favor, or equilibrium will move towards the product side. So here what did I told that if the surface excess is positive, which happens when a solute decreases the surface tension, for example surfactant, it means it will bind to the reactant or product. So if I add surfactant, it will bind to reactant, it will bind to product. But these are non-specific interactions. So in that case, what happens that since its surface area is less, its surface area is more, so binding will be stronger in case of product, and so reaction will shift towards product. What will that mean is protein is getting unfolded, or protein is getting destabilized. And the opposite way is true in the sense that if something is excluded from this, it will also excluded from this, and since this has more surface area, so exclusion will be more in the product side, and then your protein will so this reaction will move towards reactant side, which is a folded protein, and so protein gets stabilized. Is it okay? And that's why you will see that sugars, which generally do it, is used as a stabilizer of proteins. Okay, used as a stabilizer of proteins. So again, what I am trying to show you that what is the importance of this thermodynamics, and main thing is how we can affect delta G, how we can affect the equilibrium constant. That's what is the purpose of thermodynamics. Is this okay?
Yes,
I show you this is your when it is preferentially bound. So you can see there are more solid molecule near the surface in comparison to bulk. And in that case, the protein will be stabilized. Is this okay?
So over here the concentration is the concentration which we the C value of the concentration that would be of the whole square thing, right? Not the circular thing which is shown like the.
So it is concentration near the surface. I'm not about.
So then that would change, right? As the surface area increases, then the concentration of the solvent would increase around the surface as the surface area is increasing.
It is concentration. So again, you have to divide by surface.
Yes,
Am I right?
yes, sir.
So it is concentration. It is not number. Okay.
Yes.
So concentration, it doesn't mean that if area, but what I am here telling that surface excess will be positive if something is preferentially bound. That's what is the concept.
Yes, sir.
Yeah. So remember this equation dg is equal to whatever is given is equal to 0 at the equilibrium. Based on that, you can derive several equations, and that is beauty of thermodynamics. There is only two very important laws, and in fact, you can look at any chemical or physical process using those two laws. Okay. Macroscopic property. I'm discussing about macroscopic property, but you can understand each of the macroscopic property easily. You can derive yourself. It is not a very big deal. There are a lot of equations which has been proposed. I showed you one Gibbs adsorption isotherm. So whoever is studying surfactant or something like that, they need to know Gibbs adsorption isotherm. Right. So any physical process, any chemical process you can think of, how do you want to change it, how you want to make it spontaneous, you need to apply thermodynamics. Similarly, any phase transition you are discussing, material science is basically a study of phase transition. So if you don't understand thermodynamics, it is very difficult for you to. And phase diagram, I will discuss in the next a bit of phase diagram before moving to kinetics. Is this okay? Any other questions?
Sir, can you please share this PPT?
Yeah, I will share this. Okay.
Thank you, sir.
Okay, so we will discuss tomorrow.
Thank you, sir. Thank you, sir.
Thank you.
Thank you,
Sir.
sir. Thank you, sir.